Let us look at a type of group called general linear group. Such a group is one which contains elements which are matrices, and the group operation is matrix multiplication. Now, to understand this much better, we will restrict our number system to just 0, 1 for the entries in the matrices. That is z sub 2, which is nothing but integers mod 2. This general linear group is written like this: GL sub 2 of Z2, read as general linear group of 2 by 2 matrices over Z2. So this is the set A of all 2 by 2 invertible matrices over 0, 1. Now, invertible means the determinant of A is 1 mod 2. So the total number of 2 by 2 matrices over Z2 is 2 to the power of 4, which is equal to 16. Of these, 6 are invertible. So the order of GL sub 2 of Z2 is 6. Now we know a matrix is written like this, and the determinant of A is equal to AD minus BC. Now, since here we are in mod 2, so we will say AD minus BC mod 2. The required invertible matrices are those whose determinant is equal to 1. Since minus 1 is equal to 1 mod 2, that means determinant of A could be 1 or minus 1 purely based on calculation. But when we do mod 2, we will get 1. If it is something other than 1, then we ignore such matrices. Okay? So these are the 6 matrices over 0 and 1. So A1 is the identity. A2 is this, A3, A4, A5, A6. Now let's take 3 unit vectors. V1 equal to 1, 0, V2 is equal to 0, 1, and V3 equal to 1, 1. Now let's multiply A1 with V1. A1 V1 is equal to 1, 0, 0, 1 times 1, 0. Since the operation is matrix multiplication, it would be 1 times 1 plus 0 times 0, and 0 times 1 plus 1 times 0. So which gives us 1, 0, which is nothing but V1. So A1 V1 gives us V1 itself. Similarly, A1 V2 is equal to V2. A1 V3 is equal to V3. That means A1 multiplied with any of these 3 vectors gives us the vector itself. Now A2 V1. Now let's take A2. So 0, 1, 1, 0 times 1, 0, which gives us 0 times 1 plus 1 times 0, which is 0. 1 times 1 plus 0 times 0, that is 1. 0, 1 is V2. Similarly, A2 V2 gives us V1 and A2 V3 gives us V3. Now, I'm not going to do all of them one by one. So let me just show it to you like this. So A3 V1 gives us V1, A3 V2 gives us V3, A3 V3 gives us V2. A4 V1 gives us V3, A4 V2 gives us V2, A4 V3 gives us V1. So here V1, V2, V3 are the unit vectors which are permuted by the action group GL2 over Z2. Now, what can we deduce from the above? So there are exactly 6 permutations of entries in the matrices A1 to A6. There are 3 objects V1, V2, V3. Each AI corresponds to a permutation of V1, V2, V3. Now, if you think back, this looks exactly like S3 acting on an equilateral triangle. In fact, we can set up a homomorphism phi from GL to Z2 to S3. and show that it is well-defined, kernel are similar, is surjective, is injective, which means it would be an isomorphism. So we can say GL2 over Z2 is isomorphic to S3. We already know that S3 is isomorphic to D3, which implies D3 is also isomorphic to GL2 over Z2. Now, which means GL2 over Z2 has the same subgroup lattice structure as S3, since they are isomorphic. And since S3 is equal to N times H, semi-direct product, where N is a normal subgroup of S3, H is a subgroup of S3. That means GL2Z2 must also have the same semi-direct decomposition. Okay. So what do we have in GL2 over Z2? One subgroup of order 3, that is generated by either A5 or by A6, which gives us a normal subgroup containing A1, A5 and A6. And this is isomorphic to Z3. And we get 3 subgroups of order 2 generated by A2, which gives us A1, A2, which is isomorphic to Z2. Or a subgroup generated by A3, which gives us A1, A3, which is again isomorphic to Z2. Or the one generated by A4, which gives us A1, A4, which is again isomorphic to Z2. And we have the trivial subgroup, that is the I, that is the identity, which is equal to A1, and the whole group, GL2Z. So think about this. If we look at S3, you remember, we have the normal subgroup, E, R, R square, right? And we have a subgroup which we saw, E, S. So, which means A1 in S3 maps to E, A2 in S3 maps to S, A3 maps to R times S, A4 maps to R square times S, A5 maps to R, A6 maps to R square. So, which means GL2 over Z2 is equal to, there is only one normal subgroup. So, we take that as either generated by A5 or A6. The subgroup generated by A5, semi-direct product with the subgroup generated by A2 or A3 or A4. This would be isomorphic to Z3, semi-direct product with Z2. So this is general linear group. Again, let me remind you, there is a link to a PDF book which describes all these in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now.